And our first speaker is Dr. Dermot Roddy, and if you'd read the Sunday Times on Sunday, you would see him featured under the business pages in offshore coal. And Dermot is the Chief Technical Officer for Five Quarter Energy Limited. He joined Five Quarter from Newcastle University, where he was Professor of Energy, and prior to his tenure as Professor of Energy, Dermot was the CEO of Review Tees Valley. Dermot will provide an overview of the current state of development of underground coal gasification technology worldwide, and he will also outline the science and the industry knowledge behind Five Quarter Energy's proprietary technology known as deep gas winning. We await you, Dermot.
Thanks very much for the introduction. Find my slides. There is a huge opportunity in gas from rocks. One of those rocks is coal. Not surprisingly, if you start with coal, you have to have a carbon management plan. I'm not going to major on CCS because Joe Coleman talked about it, and I'm sure Angela will talk about it. But obviously, you need to do that. But to quantify what I mean by huge, if you think of all the North Sea gas we've ever landed in the UK, compute the energy content and translate it into a coal equivalent, the answer is round about 3 billion tonnes. And sitting on the UK continental shelf, you've got at least 3 trillion tonnes of coal, probably a lot more, as I've said on the slide. And whilst thinking about other rocks, there's shale rocks there as well, although I'm not going to major on that today. But offshore, we've got about 13,000 trillion cubic feet of shale gas. That compares with 5 trillion cubic feet in the Whelan shale. That's the onshore bit, which attracted so much interest all over the country about a year ago. So there's a huge opportunity, more offshore than onshore. And if you want to, I'll say a little bit later on about how you can access shale gas without fracking, although that's not the prime topic I'm talking about this afternoon. But if you'll forgive a very simplistic cartoon, just to introduce what we mean by in situ gasification of coal, you need a vertical borehole, your production borehole, and you need an injection borehole, which needs to be an arcuate well, so that you can follow the coal seam and head for the production well. You inject oxygen and steam, you ignite the coal, and then you throttle back the oxygen supply so that what you get is gasification rather than combustion. And then you're bringing a gas, which is synthesis gas primarily, to the surface. And after you've done all of that and you've finished, you cap it. And if you want to go on to this next stage, you can then say, well, we know what will happen next. It's the same as if you had mined out the coal. You'll get controlled stratal caving. Gulf is a term people tend to use for the high permeability broken rock that you end up with there. It's eminently suitable for injecting carbon dioxide into, for example. Compared with injecting it into a saline aquifer, which is more conventional, the permeability is 2,000 times greater. So you can choose to do that. And so you've got, if you like, a self-contained answer if you choose to take it to that stage. So, and any ash that was in the original coal is left behind underground. So that's the basic proposition, and people have been working on that for quite a long time in many places around the world. You're not supposed to read all the words in that slide, but you can see the countries the arrows are pointing at. So in each of those countries, something is happening at some scale in this whole field of in situ gasification of coal. If I wanted to single out the countries who have done the most of this, I would say there's Russia, there's the United States, Australia, and China. So they would stand out from the rest. An interesting thing, though, is if you look at a map of where the world's coal deposits lie, it looks nothing like the map of where the world's oil and gas deposits lie. So politically, that's very important. You're not supposed either to read the words along the bottom of this slide. Those are just named trials that have happened in various places around the world. The points that I do want to make would be you get quite a lot of variability in the composition of the gas that comes out of this process. The dark orange colour is methane, very useful for power generation. The pinky salmony colour is carbon monoxide, particularly useful if you're producing that along with hydrogen, which is the dark blue colour. Those two together would usually be referred to by chemists as synthesis gas. You can synthesize things from that. And then the light blue colour is the CO2. We need to do something about that. Now, for some people, their only interest in all of this is saying it's a gas, it burns, it can go in a gas turbine, it can generate electricity. And yes, you can do that, in which case the important metric is the calorific value, which is the solid line that crosses the graph. And that gets up to about a third of the calorific value of natural gas. Of course, since in the UK, since electricity represents only about 18% of our energy use, you don't have to burn it all and generate electricity. You can do other things as well. But there's quite a lot of variation. It depends on the depth, it depends on the coal rank, it depends on the ratio of oxygen to steam, and various other things. Another way of looking at the composition is to plot it in this form. The purpose of that graph was actually to try to tease out each point in that is a trial, but the point in this graph was to try to tease out where an economic optimum might lie. That rectangle represents an economic optimum if your business is all about power generation. If it's about something else, the economic optimum will be something different. I think it's useful to give some sense of reality to this, to look at a few photographs of where people have done this around the world. So let's start in Australia. People are doing this at the moment at a place called Bloodwood Creek in Australia. Is this my pointer? That's a small power station, 5 megawatts electrical. There you've got the production well, and there in the background you've got the injection well, and that's the whole site. So that's something which is happening in Australia at the moment. They're gasifying coal at a depth of about 200 metres. They've got nice thick seams there, 12 metres thick. We don't have those in Europe, so we have to be cleverer about our approach. Britain had a part in this one. This was the UK, Spain and Belgium did this in the late 1980s. That at its time was the deepest underground coal gasification project in the world, done at a depth of 500 metres. And that was used to pioneer some new variants on the technology. This one is back in Australia, Link Energy. They're on a much larger scale than the one I showed you before, and their end game is producing liquid fuels. So it's very much a gas to liquids play for them. And that's the deepest in the world, if you want that metric. And so they've been in Canada, they've been gasifying coal at a depth of 1,400 metres. That's as deep as anyone has got so far. So it's happening. In terms of technology, there's all sorts of things you need. You need drilling technology. I have to put in this one, it's got local interest for us. That's drilling a 2 kilometre deep borehole right in the centre of Newcastle. One of my colleagues, Paul Younger, a director of 5 Quarter and a fellow with the Royal Academy, ran that as a project. So it was for geothermal, but drilling is drilling. And so you need state-of-the-art drilling technology, even just for the vertical drilling. And then you need oil and gas industry directional drilling technology so that you can find a coal seam, follow a coal seam, home in on the production well that you're aiming for, and so on. And that's where you're using this kind of directional drilling technology, the latest version of that. And you need the right kind of onboard sensors, whether you're using tracking the Earth's magnetic field, or you're homing in on some kind of a beacon in the production well. You also need to feed data as you go, measurement data back to the surface using measurement well drilling technology. So those are the kinds of things that are all involved in this. Another aspect is when you bring a raw synthesis gas to the surface with its methane, CO, hydrogen, carbon dioxide, and anything else that's in it, you need to purify it. Now, there's nothing on this slide that a chemical engineer would say is rocket science, really. Depending on what you're trying to remove, you use one of these, and there's nothing new about water scrubbers, oil scrubbers, activated carbon beds, and so on. The challenge is to say, what is in my raw syngas, and what do I need to take out for my target end use, and then you put in what you need. You don't over-engineer it, and then you've got something which is actually affordable. So that's what you do. Now, as for what you then do, the one I should have mentioned on the way through is you have to remove CO2. But a number of people are talking about that today, so I'm not going to major on the CO2 removal, but you do have to do it. As for what you then use it for, it's very much like anybody would tell you about if they're talking about gasification, carbon capture and storage in its pre-combustion capture version. That's a very close analogue for what we're doing. And your options for what to do with the synthesis gas is, well, you can think gas to wire. I want electricity. or you can say gas to liquid fuels. There are experts in this in South Africa at a very large industrial scale. Or you can say gas to chemicals, which is the one I've really expanded on here, and said, no, you can synthesize all the building blocks for a major petrochemical and polymer chain, starting off with synthesis gas, and head for that as an end market. Now, when you think that the chemical industry is actually the largest positive contributor to the UK balance of trade, you ought to think hard about that. And remember as well that the United States, with their advantaged feedstock, which is shale gas, is now seeing a petrochemicals renaissance, leading to a manufacturing industry renaissance. This, in a whole systems context, could be hugely significant to the UK. There are two big advantages of syngas. One is flexibility and end use. That's what we've been talking about. The other one is you can store it. And we've heard a number of times today, storing electricity is difficult. Gases, we know how to store. Where it says hydrogen on here, pretend it says synthesis gas. But this is a system I used to run in Teesside where it happened to be hydrogen we were storing. But you can store synthesis gas in a system like that. Large-scale geological storage, and so you can do that. One of the things you have to get right if you're going down this path is you must make sure that you do not put contaminants into a potable aquifer. And nobody should ever do that. There are three things in this slide which individually would stop that happening. And by having all three, you've got a sort of a triple lock. The first is what I've called hydrodynamic trapping. So if you're at great depth, then rather than looking at residence times of days or years, you're looking at residence times of centuries. The water moves incredibly slowly, so you won't convect, if you like, any contaminant into a place where it shouldn't go. The contaminants you're concerned about are the ones that react, the phenols, polyaromatic hydrocarbons and so on. And there's lots of data on how far they can travel or how far they can't travel before they've actually reacted with the geology that's there. And you're typically talking about upper limits of 30 metres and so on. And so that's part of the trapping mechanism. And the other one is often referred to as a pressure arch trapping mechanism. Miners would understand that if you don't gasify the coal, but you hew it out in some other way, you're going to end up with getting extensional deformation in the overlying strata. You're going to get controlled stratal caving, and you'll start to see increased levels of porosity here. And eventually you get to a zone of net compression, which forms a pressure arch. That's what keeps the seawater out, which is why we never drowned coal miners when we were out mining underneath the North Sea, many miles out to sea. And so you've got those three mechanisms which between them and individually keep contaminants out of potable water aquifers. Everything I've said so far has been generic to the industry. I've got a couple of slides here on how we do it in 5/4, because like anybody else we think what we do is a little bit special. Looking in from the sea, you can see that first of all we're talking about being very deep. This is a cutaway to show where the coal seam that we're targeting is. But you've got many layers between the surface and where we are, and you're maybe up to 2,000 metres beneath the seabed. And then you've got your oxidant and your production well here. You've got your surface-based plant for air separation and for gas processing. You've got an injection borehole, so you're injecting your oxidant. You've got a production borehole, and so you're taking your gases out for purification. And so points of difference for us would be, we call it deep gas winning because it is deep. It's deeper than most people would do it. And the second thing is that we would operate multiple gasification chambers simultaneously without having to feed each one with its own production and an injection well. And the type of thing we're patenting is that kind of underground clever geometry that allows you to minimise the drilling costs while really scaling up the number of chambers. That's why you can afford to do it. Or if you look at, instead of looking in from the sea, if you're looking in the side elevation, you can see where we're drilling an injection borehole. We're looking several kilometres out to sea. You've got your gasification chamber here. And again, a key difference for us would be, as well as bringing out synthesis gas, we'd say we actually want to, in the immediately overlying strata, to liberate any methane that is naturally there, which is how you can get at shale gas without having to carry out hydraulic fracturing. Probably so that I've talked about. Probably the easiest way of seeing that is probably if you home in on this diagram, where I've shown that's your pressure arch. I should have maybe mentioned the way through what any mining engineer would refer to as the angle of draw. And inside that, basically, you're saying that's where you're creating mechanical disturbance. Outside of that, mechanically, chemically, nothing is going to be affected. But you're creating raised permeability in that zone. And so if you can harvest the natural native methane which is there, along with the huge amounts of synthesis gas they're producing by converting all the coal, or as much of it as you can, into a gas, then you bring really substantial volumes of gas to the surface. The ash remains here, and as long as you operate this cavity at below the hydrostatic pressure, then you should have a net flow of water in rather than a net flow of any contaminants out. So that's what we do in 5 Quarter. We call that deep gas winning, and that allows us to cost effectively scale the whole thing up to a scale which is industrially significant. As for technologies, there are a number of universities who are involved in different ways in this, but maybe of more interest, you've got all sorts of companies who wouldn't normally operate together. Some are experts in oil and gas directional drilling, some are experts in coal mining technology, some are experts in sensor technology. So there are a number of things that have to come together and come right to make this type of thing work. I've been asked to make a few comments on system-wide impacts, and a word is flexibility. I've said something about end-use flexibility of synthesis gas already, which is really what these are about. But you can have more or less drilling activity. You can have more rigs, or you can have fewer rigs. You've got some capability for geological storage, and so that's where you're getting your flexibility from, which means that depending on who you are, the government, a company or something, you can say, right, I want to optimize what should be happening in my country in the next few decades in terms of meeting the totality of the country's requirements for liquid fuels, for chemical industry feedstocks, for electricity supplies. You could even look at heating if you wanted to. So you can do that at a country level. If you build a plant with a particular emphasis, you can say, well, how do I want to optimize it over the next few years? And then I'll have my monthly plans and my daily optimization and whatnot. So it has a lot of impact on a very wide system. As for so my final slide really is, how do you do that in a particular place? Like, in pink here I've shown our first license, which is off the coast of Northumberland. We've now got 6 or 7 license areas. But if you're starting off with the 2 billion tonnes of coal that underlie those 400 square kilometres, and you notice that just down the road you've got a huge petrochemical industry and a big steel making industry with all of these point source emitters. Everything that's blue, a blue dot, is more than 1 million tonnes a year, except if it's red, in which case it's quantified. If that's your immediate hinterland, it makes a lot of sense to say the right thing to do with the gas is to use it in the petrochemical industry preferentially. In another part of the country, you would probably choose to do something a little bit different. So I'll leave it at that.
Now we come to our final speaker, Dr. Angela Whelan, the Chief Executive of Ecofin Research Foundation. And now we're talking about mobilising private sector capital for CCS in the UK. And the foundation works to accelerate the transition to a low-carbon economy. And before joining the Ecofin Research Foundation, Angela was a financial analyst specialising in the utilities and renewable energy sectors. Her presentation will address the key challenges to making CCS investable.
Thank you, John. Given that I am the last speaker and I'm the only person between the audience and the drinks, and I'm not going to really mention technology, which is, I know, very dear to your hearts, I was just thinking before this I might ask Barry if he's got another video, please, that we could perhaps put on. Last week when I was thinking about this talk, Jane from the communications department at the Academy called me up and said she was surprised I was going to talk about financing CCS because there wasn't really an industry, which is true. And in fact, you know, there are 2 potential demonstration projects. They are not up and running yet. Final investment decisions will not be until 2016. And you know, a lot of skeptics say, you know, that £1 billion that the government have committed to carbon capture and storage demonstration is not quite in the bag. But what I think is important is that we can't wait until the demonstration is underway, which may take, the construction may take, 6 years plus. It's crucial that, as Joe was saying earlier, that we get on and start to actually get the early follow-on projects going. Just before I go on, I'd like to say a bit about the Ecofin Foundation. As John was saying, the foundation was set up by the Ecofin Investment Management Company, and we feel we are not technology experts like you are, but we do invest in, well, Ecofin invests in the renewables and the energy and in the utility space. But what we strongly believed was that the thing that was missing, that someone mentioned earlier, is that policy is often made in a vacuum, and that the views of the private sector providers of capital are not often heard or understood by the politicians and the policymakers. So basically that's where we were coming from. Our current focus is on CCS development and deployment, and the Foundation's working with the ETI to help create the right conditions for this investment to happen. This afternoon I'll just quickly go through 3 things. One, I'll just set the scene a little bit for where we are with CCS in the UK, and then look at the initiatives that have been set in place, which I thought was perhaps quite interesting for this audience. So what is going on to actually drive this technology, and then finally look at some of the barriers that we've started to identify with both the financial investors and also the product developers. I think it's fair to say that although we don't have a CCS industry yet, there is plenty of ambition in the UK to create one. And I think £1 billion to be made available for 2 demonstration projects is by far the most committed approach within Europe. The Netherlands have tried and got stuck. They are significantly below what they require. There's no either private or public sector funding remaining for that, so they're in a bit of a stuck situation. The project in Norway has been halted, and that broadly leaves an EU where the member states are really not very keen to engage with this technology at the moment, apart from the UK. Rest of the world, as some of you will probably know, Canada with Boundary Dam is pushing on, and as far as we know, there are about 12 projects that are large-scale projects which are at various stages of planning in China. I think with regards to the UK, I think it's in fact got quite a disappointing history. We started off in 2007 with the first competition, launched in 2007, £1 billion again of funding, long time to get started, lots of technical complexities, high project costs, and which meant that eventually the Longannet project was withdrawn in 2011, as some people here will have been quite close to. It's interesting, around the time of this first competition, there was a UK delegation, trade delegation to China, headed by Gordon Brown, and he spoke in the Great Hall, and much to the dismay of his advisors, he then said, so this is towards the end of his term, he then said that the CCS was the UK was an international leader around the CCS technologies. At which point, apparently, his advisors sort of looked terribly embarrassed. But the China delegation said, great, how many can we have and at what price? And that sort of really kind of sums it up, that we were right there a long time ago, and if we'd pushed on with that, we'd have been a leader in the technology at this stage. But despite the failure, we've pushed on. The government launched the next stage competition. We're now down to 2 projects, White Rose in Humberside and Peterhead in Scotland. And so by the end of the decade, if all goes well, the competition projects would expect to have started operation. The argument, though, is that we need actually to push on now and make sure that we are able to plug into the infrastructure that's being developed for the competition projects with the early follow-on projects. I'd just like to say a little bit about what's happening, because some of you may not be aware of this, because it's really just just got started. Obviously, the competition will deliver some evidence of cost reductions, so we can look to them as that is pushed on with. But the cost reduction task force was set up by the government to drive commercialisation in effectively the follow-on industry. And its main conclusion is that UK gas and coal power stations equipped with CCS have clear potential to be cost competitive with other forms of low carbon generation, delivering a levelised cost approaching £100 a megawatt hour by early 2020s, and at cost significantly below that soon after. So that was their main conclusion. The task force also recommended that these three groups be set up to basically take forward the actions that they were setting out in the cost reduction task force report. These include the commercial development group that I lead, working very closely with the Energy Technologies Institute, who sponsor us to do this work, and also the Carbon Capture and Storage Association, the Trade Association for the Industry, and the Crown Estate. And the aim of this group is to secure ways with the UK government of making the projects bankable and reducing their cost of capital. The second group is, no particular order here, but the second group is the Storage and Transport Development Group, led by the Crown Estate, and the aim here is to unlock cost reductions through the benefits of scale and reduce the risk of CO2 transport and storage generally. The third group is knowledge transfer, and this group is to basically enhance cost savings potential of CCS projects by promoting and facilitating the review and flow of knowledge and information for both industry and government, following on from the early projects, so the competition projects effectively, so using them as the guinea pig in order to actually get this information out for the follow-on projects. These groups are working very closely together. It's good to see that on all groups there are stakeholders from every part of the industry, so not just the project developers, also the policy makers from DEC and the Office of Carbon Capture and Storage, and also, particularly on the commercial development group, financiers and insurers. And finally, we have here the Development Forum, which was set up very recently by Michael Fallon, working with Michael Gibbons, who's the chairman of the CCSA. And the idea is that the three groups above feed into this high-level forum, which basically advises us and monitors progress. But I think also importantly from our side is that it does give us direct access to the Minister, who is effectively championing the cause of CCS. I'll just say a little bit about the focus of the group that I'm running. As I said, and probably say many times, it is to develop CCS beyond the competition projects, which is very much in line with what the government wants, effectively to deploy cost-effective fossil fuel generation with CCS in the UK by early 2020s, which, if you're thinking about, that is at the point at which the competition projects will only be getting started. So it is important that the projects that are already there and ready to run are encouraged to do so, and that it is made possible for them to do so from an investing point of view. I think it's important just that the idea behind the competition is that it will effectively facilitate the creation of a legacy of infrastructure, so that the early follow-on projects can use this to minimise cost and investment risks. So that's why I think it's really important not to just wait and see what these demos come up with, but to actually work with them as they're going through the process, make sure that the infrastructure that is put in place, because the two projects are intended to be point-to-point, so there will be transport and storage infrastructure attached to the capture. So the idea is that you would then actually start to put the follow-on projects around this infrastructure. I know that ETI have got a very good picture of this, but I'm afraid I haven't got it here with me as to how hypothetically how that model might work. So that's the starting point, is to sort of make sure that we start to engage with this group, and this group engages with the policymakers and including the policymakers and the investors, to actually make sure that there are 4 projects that were part of the competition but were actually not successful in being part of the billion, and the others that are ready to go. And the obvious idea is that these 4 projects would plug into the infrastructure that has been developed through the competition. Some of the barriers and this is really just the start of this work. So I'm not going to give you any great solutions, but I think it's perhaps interesting just to see, what the barriers that actually these are not what we've come up with. This is what the capital, the financiers, the developers, and other stakeholders have come up with regard to what they see as stopping investment in the follow-on projects. Clearly, with energy marketplace challenges, contracts for differences under the market reform have been discussed for the renewable sector. So far, we've got no information at all about the structure and the scale of CFDs for carbon capture and storage. So that, we hope, will start to come soon. Clearly, they'll want to get the competition projects underway, but get some indication of that and some guidance would actually give the investment world something much more solid to hang on to. Regards to business structures, main concern, as you might imagine, is counterparty risk. The investment community likes things being joined up. They would much prefer it if a major player, such as GE, came and was responsible for the whole lot and kind of wrapped around it their kind of reputation. That won't happen. So you have got 3 parts of the value chain, all being run by different organizations, and it is quite a complicated process to get to the point where they are comfortable with that counterparty risk, and then the investors are sure that whatever part of the chain they're investing in, that they can be confident that their investment is not going to be affected by something completely outside of the power of the organization that they are invested in. Storage leaks are a main concern, and the liabilities and the costs around that. I have to say that the financiers were not so bothered about that when we spoke with them a while back. They, I think, are of the wrong view that somehow the government will have to take care of this liability. It may be the case, and obviously the industry would be very keen for them to do so, but there is a big issue around there about how you de-risk storage and how you share the risk, possibly between the insurance industry, the developers, and the government. The final area that actually, when I talk to DEC about this, they're always very, very surprised that there's any concern at all about the lack of confidence that the government are committed to CCS. Their view is if a government is putting £1 billion of public money up there, then this shows commitment. But I think the failure of the first competition, the fact that things have been very slow to get where they are now, that there is not any mention in the recent documentation about contacts for differences for CCS, so it's just all focused on renewables, makes them wary. And there's obviously the concern that the Treasury is still standing by, and that this £1 billion is not yet totally committed. So that is quite a strong message that we try to put to government, that they can bring the financiers with them if they actually are a little bit more open about their sort of business model for this sector and how it might work, which we haven't got yet, because I suppose understandably they've been very focused on the competition, but I think now is the time to move that focus to the follow-on projects. This just really says something which I think should be fairly obvious. Policymakers, developers, capital providers, and for an emerging major expensive, not commercial industry that you want to make happen, that these should work together. It's something that we've been quite serious about, how you get the policymakers and the capital providers to be connected. It happens a little bit more often that the policymakers and the industrialists are talking, but I suppose the encouraging thing is that the policymakers within DEC and the Office of Carbon Capture and Storage are very open about the fact that they don't really understand the financiers, and they would be pleased to have that kind of input, which I think is very encouraging. Finally, just around the sort of the goals and what we are trying to do in the development group. Firstly, as I say, it's to make sure that the financial and insurance sectors are involved and engaged with this process. Keep them informed of developments and keep the policymakers informed of what they are saying with regard to what they require or what they need to discuss with regard to making this investable, this sector. 4 of the 16 members of our steering group are from the finance sector, and through them and our own network we have access to a wider financial community as we start to sort of ramp up this input. The other 3 areas, based on the discussions with the investors, there are 3 areas. Obviously, transparency around CFDs, and this will become very important as the early projects outside the competition get going, and they need to have decisions around the funding mechanism, because they will not obviously have any capital grants. They will just be reliant on being able to access the infrastructure developed by the competition, and also then the ongoing CFD. Continued engagement between government, industry, finance sector on regulation and policy regime. That is an area we're working on, particularly around risk between the parts of the value chain and other risk areas around technology, working closely with the storage development group on that. And then finally to focus on how to construct contracts, including the detailed terms of the CFDs and the need to make projects bankable. I would hope that by this time next year that we would start to have map out some of the solutions to these barriers. We know we're already engaging with the government on the CFDs and have submitted work on that. But we're still at early stages on this, but that's just broadly where we are and what we're trying to do. Thank you.
Thank you very much. Now we'll have a short final Q&A session with Dermot and Angela. And who's going to start us off? I think, Graham, you had a very quick question.
Yes, something for Angela about the carbon capture and storage projects and the billion that the UK government are looking at putting in. When you do a first project, of course, you de-risk a market and the technology. What's the benefit to the UK? Are you looking at UK suppliers? Are you looking at UK companies? Or are we going to do that classic thing where we invest $1 billion and it's American and German companies that get all the money and experience?
The truth is I don't genuinely know where they're going to be sourcing from, but I suppose there's the immediate... I would think some of the sort of more basic stuff will be done around pipe laying, etc. I mean, so there's that advantage to the economy. In terms of the actual kit, well, I guess it will come from wherever it's best to source it from. So in the sense of, if it is cheaper and better coming from Germany or elsewhere, that's where it'll come from. And I don't know whether I don't know the inside story around that. The advantage to the UK, I suppose, given that we've sort of lost the first chance way back when we could have actually really got a head start, is that it's still very much an emerging technology at scale. And so if you actually, part of a serious full-scale demonstration that works, with all the sort of learning you get from that, then as other parts of the world catch up, then there will be some advantage in being there. But I don't know, other than actually decarbonising our economy in a way that Joe would say is the most effective way to do it. It's not sort of, I wouldn't be able to put my finger on exactly what the advantage would be around jobs, etc.
But just to throw in a little engineering example, and it's only one little part of the picture. One of the problems with transporting supercritical carbon dioxide over long distances is that you get a rapid crack propagation mechanism in pipelines, and the way they get around it in the United States is they grossly over-engineer that pipeline, and they can afford to do that because they sell the CO2 for a lot of money for enhanced oil recovery. We can't do that. And so you've got world-leading expertise in how to design a pipeline that can carry contaminated supercritical CO2, and nobody else has got that technology yet. So in areas like that, we're forced to actually develop something which is world-beating. And as long as we don't slow down, then that would be just one little example, an engineering type example of where the UK can actually make a killing.
I think the US have just given a go-ahead actually to a zero-emission power station in the US. Which should be ready in 2 years' time. So the fact is that between the Chinese and the Americans, I think they'll get ahead of us, is my feeling, sadly. I hope that's not the case, but the financial imperative might make it so, ultimately.
Talking about the advantages to UK, James Martin of McDonald, there is a price of oil at which the enhanced oil recovery of carbon sequestration actually starts to pay off. Now we've got two experts on the panel there to talk about the enhanced oil recovery. That could be a huge bonus for recovering the remaining oil in place from the North Sea. Would you like to estimate what the price of that oil is in dollars per barrel at which it breaks even?
You need to make your plans based on $50 oil or $60 oil and so on, and various cost curves cross over there. What I find people don't talk about is they don't talk about enhanced gas recovery. And I'm really surprised. A lot of people speculate about what might be the economic cost for enhanced oil recovery. Quite often the depleted gas fields are closer to us. It's cheaper to inject into them. You don't necessarily have to use supercritical CO2, and yet it doesn't even get mentioned, never mind quantified. So I think there's a huge opportunity. Now, if you want to store huge volumes of CO2, then what you do is you start off when your plants are expensive, your first of a kind plants, running those in enhanced oil recovery mode. But there's something like 100 times as much saline aquifer storage as there is storage in depleted oil and gas fields, and so eventually that runs out, and then you hope that by that stage the cost of carbon capture and transportation has go down to the point where you can do without the extra money that comes from the EOR or the enhanced gas play.